For a brief moment one distant planet seemed to carry the smell of life. Not the sound of a signal, not the shape of a city, not a radio message crossing the dark, just a faint mark in starlight, a tiny wound in a spectrum from a world so far away that every fact about it has to be extracted from almost nothing. A planet orbiting a dim red star in the constellation Leo, a planet too distant for any camera to see as a globe, a planet whose sky, if it has one in any Earth-like sense, will not be visited by any human machine for a very long time, and yet for a little while, K2-18b felt close. Close enough to make headlines. Close enough to make people pause. Close enough for one question to move from science fiction into the uneasy language of observation. Had we just seen a trace of life? The answer was never yes. But it was not nothing either. That was the danger of it. The story did not begin with a photograph of an ocean world. There was no image of blue water under alien clouds, no distant shore, no living surface glowing under a red sun. K2-18b gave us something colder and more difficult. A curve of light, a handful of wavelengths, a possible chemical fingerprint in an atmosphere. More than 100 light-years away, for most people, that sounds too small to carry the weight of hope. For astronomers, it can be everything. And when a planet passes in front of its star, a little of the star's light filters through the planetmosphere before reaching us. The planet blocks most of the starlight with its dark body, but the thin ring of atmosphere around its edge leaves a trace. Molecules in that atmosphere absorb specific colors. They do not write words, they do not announce themselves, they remove tiny pieces of light. A spectrum is what remains. A kind of barcode. The dream is that one day, in one of those barcodes, we will see a pattern that cannot be explained by geology, chemistry, or noise alone. Something that points toward biology. Something that suggests the planet is not merely another world, but a living one. K2-18b became famous because, for a moment, one part of its barcode seemed to whisper the name of a molecule that on Earth is deeply tied to life, dimethyl sulfide DMS, a sulfur-bearing gas produced in large amounts on Earth by marine microorganisms, especially processes connected to phytoplankton and ocean life. A molecule that has the wrong emotional shape for history. It is not grand, it is not poetic, it is not the kind of word that belongs in a headline. It sounds like laboratory language, the kind of thing hidden in a chemistry paper, but if you are searching for life in the universe, even an ugly molecule can become beautiful. DMS does not prove life. Even on Earth, a molecule's biological association does not make it a universal law. Alien planets can have unfamiliar chemistry. Atmospheres can confuse us. Spectra can mislead us. Models can fit the same data in more than one way. Still, the idea was intoxicating. A planet in the habitable zone. A hydrogen-rich atmosphere. Methane and carbon dioxide. A possible ocean world interpretation. A possible biosignature gas. For a brief moment, the pieces seemed to arrange themselves into a shape almost too powerful to ignore. A living ocean planet. That was the image that escaped into the public imagination. Not because scientists had proven it, they had not. Not because the data demanded it, they did not. But because human beings are very good at turning uncertainty into a picture, the picture was irresistible. K2-18b under a red dwarf star. A deep global ocean beneath a thick atmosphere. A warm, strange world larger than Earth, smaller than Neptune. Clouds moving over an alien sea. Life somewhere in that water, releasing gases into the air, leaving a faint mark that crossed space and entered the mirror of the James Webb Space Telescope. It was the kind of story science has taught us to want, not a flying saucer, not a face on Mars, not a signal from a civilization, a chemical clue, quite remote, almost believable. That is why the fall mattered, because the signal did not collapse like a hoax. It did not explode into scandal. It did not vanish in a dramatic confession. It was subjected to something more brutal and more ordinary: reanalysis, disagreement, statistics, models, instrument noise, alternative explanations. and the cold patience of evidence. The most beautiful hope in astronomy had to survive contact with the data. And it struggled. K2-18b is not Earth. That sentence should sit at the center of the story, because nearly every misunderstanding begins by forgetting it. The planet is often described as being in the habitable zone of its star, and that phrase carries too much warmth. The habitable zone does not mean a planet is habitable. It means that, under some atmospheric conditions, temperatures could allow liquid water on a surface. It is a starting point, not a verdict. K2-18b orbits a red dwarf star known as K2-18. It is far larger and more massive than Earth, in a class often called sub-Neptunes or mini-Neptunes. Worlds like this do not exist in our solar system. That is a problem. Earth has neighbors we can touch with spacecraft and compare with geology. Mars, Venus, the giant planets, icy moons, asteroids, they give us physical examples, but sub-Neptunes are common around other stars and absent at home. We know they exist in large numbers. We do not know them intimately. K2-18b is one of these unfamiliar worlds. It may have a thick, hydrogen-rich atmosphere. It may have a deep volatile envelope. It may have high pressures and temperatures beneath that atmosphere. It may have conditions compatible with a liquid water ocean. It may instead be a world whose interior is far less friendly than the word ocean suggests. The planet is not a blue marble waiting for a sharper lens. It is a problem. That problem became more interesting when observations suggested molecules in its atmosphere. Earlier studies raised attention by reporting water vapor or water-related atmospheric features. Later, the James Webb Space Telescope gave scientists a stronger tool. Webb was designed to see infrared light with extraordinary sensitivity. It could watch K2-18b transit its star and measure how the planet's atmosphere altered starlight. The 2023 Webb observations became a turning point. They showed evidence for carbon-bearing molecules, including methane and carbon dioxide. That alone was important. Methane and carbon dioxide in a hydrogen-rich atmosphere around a temperate sub-Neptune are not small. They help scientists understand what kind of atmosphere the planet might have, what chemical pathways may be active, and whether certain planetary scenarios are plausible. The same work also mentioned a possible hint of DMS, not a confirmed detection. A hint, in science, that word should slow the blood. In public imagination, it often does the opposite. A hint is not nothing. It can be the beginning of a discovery. Many real discoveries begin as weak features that grow stronger with better data. But a hint is also where error loves to hide. Noise can look like a feature. A model can prefer a molecule that is not really there. An instrument can carry patterns that are not planetary. A choice in data reduction can tilt a result. A planet's atmosphere can contain other molecules whose absorption overlaps with the molecule we want to find. A hint is a door that may open onto a room, or onto a wall painted like a room. The DMS hint in K2-18b was exciting because of its biological association on Earth. In our own oceans, DMS is linked to marine life and sulfur cycling. It can rise from the sea into the atmosphere. It is part of Earth's living chemistry, but Earth is not the universe. A gas that is biological here may not be exclusively biological everywhere. A gas that is rare here may be produced differently under alien conditions. A spectral feature that resembles one molecule may be produced by another. When the planet is 124 light-years away, when all you have is the light of a star filtered through a thin atmospheric rim, certainty becomes expensive. That cost is what the public rarely sees. A headline can travel instantly. A spectrum takes months of work. A claim can sound clean. The data underneath it may be fragile. K2-18b became the stage for that tension. The next wave of attention came with new observations, using Webb's mid-infrared instrument. The claim became stronger in language, though still careful in the formal scientific sense. Researchers reported new constraints and possible evidence for DMS and/or another sulfur-bearing molecule, dimethyl disulfide, DMDS. The statistical significance was discussed as being around the level that makes scientists pay attention, but does not settle the matter, in the way a historic life claim would require. The public heard something else. Strongest evidence yet, potential biosignature, alien life clues, ocean world. Those phrases spread faster than the caveats. For a week, the planet seemed to glow. Newsrooms love a story that sits between humility and revelation. Scientists did not say they had found life. That made the story safer, but they also did not say the signal was meaningless. That made it thrilling. The result hovered in a perfect media zone. Not proof, but possibility. Not discovery, but the strongest hint. Not aliens, but chemistry associated with life on Earth. The ambiguity became the headline. Some people heard not proof and understood caution. Many people heard strongest evidence yet and felt the old dream awaken. The dream has a long history. Every generation has wanted the universe to answer back. Mars once carried canals in the human imagination. Venus once carried jungles under clouds. Radio astronomy carried the possibility of deliberate signals. Meteorites, organic molecules, methane on Mars, phosphine on Venus, strange dips in starlight, interstellar objects, unexplained spectra. Again and again, the search for life has moved between hope and correction. K2-18b arrived in that same emotional lineage, but with a more modern face. It was not a blurry telescope image. It was not a myth of little green men. It was spectroscopy from the most powerful space telescope ever launched. That made the hope feel adult, respectable, almost safe. But the universe is not obligated to reward respectable hope. The scientific pushback began quickly, and it was not all the same. Some researchers questioned the robustness of the DMS and DMDS feature. Others examined whether the same data could be explained without those molecules. Some focused on how the data were reduced and binned. Some looked at the statistical strength of the detection. Some warned that even if the molecule were present, a biological origin would still be a much larger and harder claim. Others questioned whether K2-18b was truly a Hycean world at all. That word, Hycean, deserves care. It is one of the most powerful ideas in modern exoplanet science. A planet with a hydrogen-rich atmosphere and a global ocean, possibly habitable under the right conditions. The name fuses hydrogen and ocean, and the image is immediate. A larger-than-Earth planet, wrapped in hydrogen, with a deep sea underneath. For K2-18b, the Hycean interpretation became central to the excitement. Methane and carbon dioxide, along with the absence or low abundance of ammonia, were discussed as consistent with some predictions for a Hycean atmosphere. If the planet had a liquid ocean, and if it had a hydrogen-rich atmosphere, and if DMS or DMDS were present, then the life question became sharper. But Hycean is not a photograph, it is a model. A model can be useful, elegant, and wrong, or partly right, or right for the wrong reasons. K2-18b may not have a surface ocean in the way people imagine. It may be a mini Neptune with a thick atmosphere and hostile conditions below. It may have high-pressure layers or interior structures that prevent a habitable ocean surface. Its atmosphere may fit multiple scenarios. The same broad measurements can support competing stories. This is the problem with planets that cannot be seen directly. The world is not handed to us. It is reconstructed. And reconstructions depend on assumptions. How much cloud or haze is present? What is the temperature structure? What molecules are allowed in the model? What pressure levels are being probed? What is the planet's bulk composition? How does stellar activity affect the observation? How do instruments behave? How are spectral data processed? Which wavelength regions are trusted? Which statistical thresholds count as compelling? The public wants the planet. Science has the model. The model began to tremble. One of the sharpest lessons from the K2-18b controversy is that a spectral feature is not a molecule in a bottle. No one flew to K2-18b and captured air. No one watched DMS drift through clouds. The molecule was inferred from how light changed at certain wavelengths. That inference depends on comparing observed spectra with predicted spectra from atmospheric models. If DMS absorbs light in a certain region, and the data show a feature in that region, DMS becomes a candidate, but there may be other candidates. Instrumental effects can mimic structure. Noise can create apparent bumps and dips. The data may be sensitive to binning choices. Other molecules can have overlapping absorption features. Clouds and hazes can flatten or distort spectra. The host star itself can complicate the signal, especially for planets around active red dwarfs. Because spots and bright regions on the star can change the light before the planet's atmosphere ever gets involved. The planet's atmosphere is not the only thing between the telescope and truth. There is the star. There is the telescope. There is the instrument. There is the pipeline. There is the model. There is the human desire to see meaning. Each layer can introduce error. That does not make the search hopeless. It makes it hard, and K2-18b became a lesson in hard. As independent researchers revisited the data, the life signal began to look less secure. Some analyses reported insufficient evidence for DMS and DMDS. Some found that the claimed features did not reach robust statistical significance when the data were handled differently. Some argued that the spectrum could be consistent with other explanations. Later critiques emphasized that K2-18b did not meet the standards required for evidence of life. The phrase "fell apart" does not mean every observation was worthless. It means the interpretation that excited the world could not carry the weight placed on it. Methane and carbon dioxide remained important. K2-18b remained scientifically fascinating. The planet did not become boring because the biosignature claim weakened. But the dramatic leap, from spectral feature to possible life, became much harder to defend. This is how science protects itself from its own longing. A weaker culture would keep the beautiful story. Stronger one lets it bleed. There is grief in that, not personal grief, not tragedy, but a quieter kind of scientific disappointment. For a few days, people imagined that the search for life had crossed some invisible threshold. The universe felt less empty. The distance between Earth and another living world seemed to shrink. Then the caveats returned. Then the models returned. Then the statistics returned. Then the signal cooled. And K2-18b became not the planet where life was found, but the planet that showed how difficult finding life will be. That may be its real importance, not a discovery of life. A rehearsal for the discovery of life. Because one day, if the detection comes, it may look uncomfortably similar at the beginning. Not a spaceship, not a message, not an image of forests, a spectrum, a small feature, a molecule, a debate, a team making a claim, other teams pushing back. New observations, stronger data. Alternative explanations falling away or refusing to fall away. The real discovery may not arrive as a clean announcement. It may arrive as a long argument that slowly runs out of good objections. K2-18b teaches us that life is not a word science can afford to use cheaply. A biosignature is not a magic molecule. Oxygen can be produced biologically, but it also has possible abiotic pathways under some conditions. Methane can be biological, geological, or photochemical depending on context. DMS is deeply associated with biology on Earth, but an alien atmosphere is not obligated to obey Earth's categories. Even if a gas is detected, the biological interpretation must compete with non-biological explanations. A true life claim would need context, planet type, atmospheric composition, temperature, pressure, stellar environment, photochemistry, clouds, ocean evidence, geology if accessible, multiple molecules, chemical disequilibrium, repeat observations, independent confirmation, instrumental checks, models that survive hostile testing. One molecule, especially a disputed one, is not enough. That sentence is not designed to kill wonder. It is designed to preserve wonder from becoming a lie. The dream of K2-18b was beautiful, because it was close to the kind of evidence we may someday use. The collapse was painful because it showed how easily a signal can become overinterpreted. The lesson is not to stop searching. The lesson is to raise the standard until the answer can survive being attacked. Every serious biosignature claim must be treated as if it is wrong. Not because scientists are cynical. Because the stakes are too high. If humanity declares life beyond Earth, and then has to retreat, the damage is not only embarrassment. It weakens trust. It trains the public to hear every future claim as hype. It turns the most profound scientific question into a media cycle. The universe deserves better than that. So does the public. K2-18b was discovered during the Kepler mission's extended K2 phase. It orbits its star in roughly a month, close enough to its red dwarf that it receives a level of energy that places it within the broad habitable zone conversation. But red dwarfs are not gentle suns. They can flare. They can have stellar activity that affects planetary atmospheres. Their small size helps astronomers study transiting planets because the planet blocks a larger fraction of starlight, but the same stars can complicate the interpretation. A planet around a red dwarf can be easier to observe and harder to understand. K2-18b's size also complicates everything. It is not a rocky Earth twin. Its radius and mass suggest a world with substantial volatile material, a thick atmosphere, or layers unlike Earth's. A planet like that may have a deep ocean. It may have a crushing atmosphere. It may have no true surface in the way we imagine. It may transition through exotic high-pressure phases. It may be habitable only under specific conditions, or not at all. The public image of an ocean world often borrows from Earth: waves, clouds, a surface where life blooms. A sub-Neptune ocean world, if it exists, may not feel like Earth. It could be covered by a thick hydrogen atmosphere, where pressures rise rapidly. Its ocean surface, if present, may sit under an atmosphere very different from ours. Its temperature structure may depend on greenhouse effects, albedo, atmospheric circulation, and chemistry. Its interior may be shaped by high-pressure water phases or deep layers that are not familiar from Earth. The word ocean can seduce us into thinking we understand the planet. We do not. That uncertainty was part of the scientific fight. If K2-18b is not Hycean, the DMS story changes. If it is a mini Neptune without a habitable ocean surface, a biological interpretation becomes much weaker. If its atmosphere is shaped by processes that mimic the molecules of interest, the signal loses force. If clouds, haze, stellar contamination, or alternative gases explain the spectrum, the life story dissolves. The planet did not have to be dead for the claim to fail, it only had to remain ambiguous. Ambiguity is enough. A historic detection cannot rest on ambiguity. The James Webb Space Telescope did exactly what it was built to do in this story. It opened a new window. It allowed scientists to study atmospheric features of a small, temperate exoplanet in ways that were nearly impossible before. Webb made the debate possible. That is often missed. When a controversial result weakens, people sometimes blame the instrument, or assume the whole effort failed. But a powerful telescope does not guarantee simple answers. It gives science sharper tools, and sharper tools reveal complexity. Webb did not make K2-18b easy. It made K2-18b arguable. That is progress. Before Webb, many of these atmospheric questions would have been unreachable. With Webb, they become difficult but real. We can ask whether methane is present. We can ask about carbon dioxide. We can search for weaker molecules. We can compare instruments and wavelengths. We can test models. We can argue with data instead of speculation. A signal that falls apart can still teach more than silence. K2-18b's life signal became weaker under pressure, but the process sharpened the entire field. Scientists learned which observations are not enough. They learned how sensitive conclusions can be to data processing. They learned how dangerous it is to let a potential biosignature outrun planetary context. They learned how quickly media framing can exceed the evidence. the next claim will be judged more harshly because of K2-18b. That is good. Life beyond Earth should be hard to claim. The history of science is filled with beautiful errors. Some are foolish, some are understandable, some are necessary steps toward truth. A weak signal can inspire better observations. A wrong interpretation can expose missing physics. A failed claim can force better standards. K2-18b may become one of those cases. Not a scandal, not a dead end, a warning light. The planet itself remains out there, unchanged by our excitement and disappointment. It continues orbiting its red star. Its atmosphere, whatever it contains, continues absorbing starlight. Its clouds, if present, continue forming and dispersing under alien conditions. Its chemistry continues without regard for headlines. The human story changed, the planet did not. That is another humbling part of astronomy. The objects we debate are not participating. K2-18b did not almost reveal life, then hide it again. It did not tease us, it did not fail us. We saw a faint pattern and built meanings around it. The data were always what they were. The collapse happened here, in models, in papers, in headlines. In imagination, the planet remained silent. The silence is the point. Most of the universe is silent to us. Not empty, necessarily, silent. It does not speak in human categories. We translate physical processes into stories because that is how minds hold complexity. But the translation can overreach. A spectrum becomes a scent. A molecule becomes a biosphere. A biosphere becomes an almost discovery. Then science pulls the story back toward the measurement. That pull can feel cruel. It is the only way to keep truth possible. Imagine the scene not as a press conference, but as a control room of patience. Astronomers wait for a transit. K2-18b moves across the face of its star from our point of view. The star dims by a tiny amount. For a few hours, Webb collects light. The planet's atmosphere, if it is transparent enough at certain wavelengths, filters a fraction of that light. The signal is tiny, the star is active, the instrument has its own behavior. The data must be calibrated, noise must be modeled. The spectrum is extracted. There is no single moment where a molecule appears glowing on a screen. There is reduction, correction, fitting, retrieval, comparison, uncertainty. Scientists build atmospheric models with different combinations of molecules, clouds, temperatures, and abundances. They ask which model best fits the observed spectrum. They compute statistical preferences. They test whether a feature is real or noise. They compare with other instruments. They ask whether the same explanation survives when assumptions change. This is not glamorous. It is the machinery behind wonder. Without that machinery, wonder becomes superstition. The public often sees the end of the process as a headline. But in a case like K2-18b, the end never really arrived. The headline came before the process was finished. That is not unusual. Scientific publishing and media attention have different metabolisms. Science moves through uncertainty.
Media feeds.
K2-18b became a moment. The planet almost looked alive because the story had the right ingredients. A habitable zone world, a powerful telescope, a molecule associated with life, and a name that sounded technical enough to be real. There was no cartoon alien nonsense. That made it more persuasive. It felt like the mature version of the alien life story, the one we had been waiting for since childhood myths burned away, a distant atmosphere, a biosignature gas, a cautious scientific claim. The problem was not that the story was silly. The problem was that it was premature. Premature hope is not harmless. It changes how people remember the evidence. Even after the signal weakens, the original impression remains. Many will remember that life was almost found on K2-18b. Fewer will remember the details of the reanalysis. The correction moves slower than the excitement. That is why wording matters. A possible biosignature is not a biosignature detection. A tentative detection is not a confirmed molecule. A molecule associated with life on Earth is not evidence of life elsewhere by itself. A habitable zone planet is not necessarily habitable. A Hycean candidate is not a proven ocean world. A spectral fit is not a photograph. Each phrase is a guardrail. Roam the guardrails, and the story falls into fantasy. But keep too many guardrails, and the public may never feel the wonder. That is the delicate work. To tell the story with enough emotion to make people care, and enough restraint to keep the story honest. K2-18b deserves that balance, because even after the life signal weakened, the planet remained extraordinary. It is one of the best laboratories for studying temperate sub-Neptune atmospheres. It shows that Webb can probe molecules around worlds far smaller and cooler than the hot giant planets that once dominated exoplanet atmospheric science. It forces scientists to develop better models for hydrogen-rich atmospheres, possible ocean worlds, cloud decks, hazes, and photochemistry. It pushes the question of habitability beyond Earth-sized rocky planets. The planet is still a doorway, just not the doorway some headlines promised. That distinction matters. When a claim collapses, the public often swings from overbelief to dismissal. It was life, then it was nothing. It was a breakthrough, then it was hype. But science lives between those extremes. K2-18b is not proof of life. It is also not irrelevant. It is a difficult, important planet whose atmosphere may teach us how to search better. The fall of the life signal does not erase the value of the search, it clarifies the search. The phrase standards of evidence for life sounds dry until you feel what is being protected. To say that a planet does not meet those standards is not to mock the original excitement. It is to insist that the greatest claim in science cannot be built on a weak foundation. The foundation must hold under hostile testing. It must survive alternative models. It must be repeated. It must be understood in planetary context. The discovery of life beyond Earth would be too large for ordinary confidence. It needs extraordinary patience. K2-18b did not meet that bar. That does not mean no future exoplanet will. In fact, K2-18b may help us recognize what a stronger case should look like. A stronger case might involve multiple independent observations across different wavelengths, all pointing to the same atmospheric composition. It might involve a suite of gases that are difficult to maintain together without biology under the planet's conditions. It might involve a planetary environment whose habitability is independently supported, not merely assumed. It might require ruling out stellar contamination, instrument systematics, clouds, haze, and non-biological chemistry. It might require future telescopes beyond Webb. The real detection may be cumulative. Not one molecule, not one headline. A structure of evidence. K2-18b showed us what a weaker structure looks like. It looked beautiful from a distance. Then weight was placed on it. Then the cracks appeared. There is no shame in cracks appearing. That is what tests are for. The shame would be pretending they are not there. A culture that wants real discovery must learn to love the moment when a beautiful idea is challenged. It must see skepticism not as betrayal, but as the method by which fragile claims become strong or disappear. Skeptics did not ruin K2-18b. They did what the search for life requires. They asked whether the light really meant what people hoped it meant. The answer for now is no, or more precisely, not enough. Not enough to claim DMS robustly, not enough to claim DMDS robustly, not enough to claim biology, not enough to claim an inhabited ocean, not enough to call it life. Those words are disappointing. They are also honest. The planet remains a candidate for study, not a world transformed by discovery. There is still something haunting in that. For a few days, the human mind stood at the edge of a threshold. The threshold did not open. But now we know the shape of it better. We know that the path will not be simple. We know that alien life, if found through atmospheres, will probably enter science as a contested signal, before it becomes a settled fact. That means the public will need to mature with the science. We will need to learn how to live with probabilities, with weak features, with disputed molecules, with headlines that cool, with claims that rise and fall. With the difference between exciting and true, K2-18b is a training ground for that maturity. It asks whether we can want life beyond Earth without forcing the universe to give it to us early. The answer is not obvious. Human beings are not neutral observers. We have loneliness built into the question. The search for life beyond Earth is not like measuring the mass of a moon or the temperature of a star. It touches identity. If life exists elsewhere, Earth becomes one example among many. If it does not, or if it is extremely rare, Earth becomes more fragile and strange. Either answer changes the emotional architecture of being human. So when a planet like K2-18b hints at life, even weakly, people lean forward. The leaning is understandable, but leaning is not evidence. The universe has fooled us before. Venus phosphine became a cautionary tale for biosignature claims. A possible detection of phosphine in Venus's atmosphere was announced, widely discussed, challenged, reanalyzed, and complicated by questions about data processing, spectral features, sulfur dioxide, and instrument calibration. The debate did not end the search for life in Venus's clouds, but it showed how quickly a molecule can outrun its evidence. K2-18b belongs to that same lesson. Molecules are not miracles. They are claims embedded in noise. The more remote the planet, the harder the claim. Venus is next door in planetary terms, and even there the debate became messy. K2-18b is more than 100 light-years away. We cannot send a probe into its atmosphere. We cannot sample its clouds. We cannot map its surface. We cannot watch weather systems form over oceans. We have transits, spectra, models, and patience. The distance is not just physical, it is epistemic. It is a distance in knowledge. Every conclusion must cross that distance carefully. That is why K2-18b's story should not be told as a scandal of hype, but as a drama of uncertainty. The original researchers pursued a real question with real data. The critics responded with real analysis. The media amplified some parts more than others. The public received a simplified version. The planet remained unresolved. This is not a story of good science versus bad science. It is a story of science under pressure from hope. That pressure will only grow as instruments improve. Webb has already changed exoplanet astronomy. Future observatories may go further, studying smaller worlds, cooler planets, more Earth-like atmospheres, better spectra. The closer we get to possible biosignatures, the more emotionally volatile the claims will become. K2-18b is a preview, not the end of the search. The beginning of a harder era. In the old era, alien life was mostly imagination. In the new era, it may be an atmospheric retrieval problem. That sounds less romantic until you understand the stakes. A few missing wavelengths from a star may one day tell us that a living planet exists beyond the solar system. But those same missing wavelengths may also lie, not intentionally, not maliciously. They may lie because noise looks like structure, because molecules overlap, because stars are imperfect backgrounds, because instruments are physical machines, because models are incomplete, because human beings want the answer. The search for life is the search for a signal that can survive all of that. K2-18b's signal did not survive well enough. The world went back to being a question mark. But question marks are not empty. A good question mark is one of the most valuable things in science. It focuses attention. It exposes ignorance. It guides better observations. It forces methods to improve. K2-18b remains a sharp question mark at the edge of what Webb can do. What is its atmosphere really made of? Does it have clouds or haze? Is it Hycean or something less hospitable? Are methane and carbon dioxide telling us about a water ocean, or about a different kind of sub-Neptune chemistry? Are there trace gases beyond current confidence? How much can JWST reveal, and where does it reach its limits? The planet may become less famous as the life headlines fade, but scientifically it may become more useful. Fame is noisy. Usefulness is quieter. K2-18b is a quiet giant now, orbiting a small red star, still absorbing light, still waiting for better observations. The phrase, life signal that fell apart, is dramatic, but the falling apart was not a collapse into nothingness. It was a collapse into complexity. The story, possible DMS means possible life, broke open into a more demanding story about atmospheric retrievals, planetary classification, statistical thresholds, false positives, and the philosophy of evidence. That more demanding story is harder to sell. It is also closer to the truth. The life we seek may not make itself obvious. It may not announce itself with one clean molecule. Even Earth viewed from far away would require careful interpretation. Our atmosphere contains oxygen, methane, water vapor, carbon dioxide, ozone, and other clues, but the strength of Earth as a living planet comes from context and disequilibrium, not one molecule alone. If aliens studied Earth with limited data, would they be certain? Maybe not at once. They would need repeated observations. They would need models. They would need to understand the sun. They would need to see seasonal changes, atmospheric chemistry, surface reflectance, maybe signs of oceans and continents if their telescopes were good enough. They would need to rule out abiotic pathways. Even Earth might begin as a debate. That thought should make us patient with K2-18b. A real living planet may be hard to prove. A planet that is not clearly living may be even harder to disprove. Between those two difficulties lies the future of astrobiology. K2-18b's public moment was built around DMS and DMDS. The names are similar, and in the spectrum they can be difficult to separate depending on the wavelength, range, and data quality. Both are sulfur-bearing organic molecules. On Earth, DMS is strongly associated with biological processes, while DMDS can also be related to biological and chemical sulfur cycles. In an exoplanet atmosphere, detecting either requires disentangling faint absorption features from other possible contributors. A small shift in interpretation can change the whole story. DMS as a confirmed molecule would be exciting. DMS as a tentative fit is interesting. DMS as a model-dependent feature is uncertain. DMS as noise is nothing. DMS as an abiotic product is not life. The same letters can carry different meanings depending on evidence. That is why scientists insist on statistical significance. A feature must rise above noise. It must be unlikely to appear by chance. It must remain under different ways of processing the data. It must not disappear when assumptions change. It must not depend on one fragile choice. The threshold for ordinary molecular detection is already demanding. The threshold for life should be harsher. Some discussions compare levels of statistical confidence, but numbers alone do not settle the deepest issue. A 3 sigma signal may be worth attention, but a life claim requires more than a statistical bump. It requires understanding whether the molecule is truly there, and what it means in that planetary environment. The same statistical value can feel different when attached to water vapor, methane, DMS, or life. A possible biosignature is not just a detection problem. It is an interpretation problem. The atmosphere of K2-18b may contain methane and carbon dioxide with more confidence than the sulfur molecules. Those gases themselves raised interest because they fit some Hycean models. But even there, the story is not simple. Methane and carbon dioxide can exist in non-living atmospheres. They are important clues, not biological signs by themselves. Their presence helps constrain the planet's atmosphere. But it does not decide habitability. The absence or low abundance of ammonia was also discussed in the Hycean interpretation. In some models, ammonia should behave differently, depending on whether the planet has an ocean and certain atmospheric conditions. But model-dependent interpretations must be handled carefully, especially for a class of planet we cannot compare to one in our own solar system. This is the recurring issue. K2-18b sits in a region where our imagination is strong and our examples are weak. That is dangerous. It is easy to fill the gaps with Earth-like images. a red sun over a global ocean, marine microbes, a gas, rising from water into air. But the real planet may be stranger, harsher, less oceanic, less habitable, or chemically misleading. It may not be less interesting, only less convenient. A thick hydrogen atmosphere can allow a planet farther from intense stellar heat to maintain warmer conditions beneath, but it can also create enormous pressure. A planet larger than Earth may hold onto a massive envelope. Under that envelope, the boundary conditions for an ocean may be extreme. High pressures can create phases of water and ice unknown at Earth's surface. Interior heat can alter the picture. Clouds and haze can hide deeper layers. The public phrase ocean planet is too clean. The real K2-18b could be a layered, pressure-dominated, chemically complex sub-Neptune, where the question of a habitable surface is not settled. That is not a failure of imagination, it is what makes exoplanets real. They are not required to fit the categories that make good thumbnails. And yet thumbnails matter because attention matters. Without attention, many people would never learn that scientists can study atmospheres across interstellar distances. Without excitement, the search for life becomes buried in technical literature. The problem is not emotion. The problem is emotion outrunning evidence. The better story is not less dramatic, it is more dramatic. A planet almost looked alive, then the signal weakened under scrutiny. That is not boring. It is a scientific tragedy in miniature, and also a triumph. The tragedy is the loss of a beautiful possibility. The triumph is that the method worked. The claim was not simply accepted because people wanted it. It was attacked, tested, and forced to shrink. That is how we avoid fooling ourselves. The search for life is haunted by false positives. A false positive is not merely a wrong answer. It is a convincing wrong answer. A signal that looks like life but is not. Oxygen from water loss around certain stars. Methane from geology. Phosphine from misunderstood chemistry or data effects. Organic molecules from non-biological processes. DMS from pathways not yet fully understood in exotic atmospheres, or not present at all but mimicked by another feature. The universe can make many things without life. Life is not the only chemist. A proper biosignature must be hard for non-living processes to imitate in that specific environment. That last phrase matters. In that specific environment, a gas that seems biological on Earth may be abiotic elsewhere. A gas that is abiotic on one planet may be biologically suggestive on another. Context is not decoration. Context is the claim. K2-18b lacked enough context. That is why the signal fell apart, not because DMS is uninteresting. Not because Webb failed. Not because scientists were foolish to look, because the path from molecule to life had too many missing stones. At times, the public debate treated skepticism as pessimism. That is a misunderstanding. Skepticism in astrobiology is not a refusal to believe life exists elsewhere. It is a refusal to confuse desire with discovery. Many skeptics want life to be found as much as anyone. They simply know that the moment must survive history. Imagine being part of the generation that announces life beyond Earth. The responsibility would be immense. Every textbook would change. Every religion, philosophy and culture would respond in its own way. The question would move from speculation to fact. The scientific claim would have to survive not only peer review, but decades of scrutiny. No responsible scientist should want to be early and wrong. K2-18b was a warning against being early, not against being bold. Boldness is necessary. Someone had to propose Hycean worlds. Someone had to examine K2-18b's atmosphere. Someone had to search for DMS. Someone had to publish the models and take the risk of being challenged. Without bold claims, science can become too cautious to move. But boldness must invite attack. The strongest ideas are not protected from criticism. They are strengthened by surviving it. The DMS/DMDS claim did not survive strongly enough. That does not make it worthless. It makes it provisional, contested, and insufficient for life. There is still room for future observations to change the picture. More transits, better signal-to-noise, refined data processing, improved molecular line lists, broader wavelength coverage, and independent teams could reveal whether any sulfur-bearing molecules are really present. A future result might strengthen the case, or it might bury it. Science has not closed the file, it has downgraded the headline. That distinction should be kept. K2-18b is not dead as a scientific target. The life claim is simply not alive, in the way the public briefly imagined. The planet continues to matter, because temperate sub-Neptunes may be common in the galaxy. If some are habitable, the number of potential life-bearing worlds could be enormous. If most are inhospitable despite sitting in habitable zones, then our search strategies must change. K2-18b is part of figuring out which is true. It is a test case for a whole class of worlds. That may be more important than one disputed molecule. Exoplanet science began with strange giant planets orbiting close to their stars, worlds no one expected. Then came super-Earths, mini-Neptunes, compact systems, lava worlds, inflated gas giants, planets around red dwarfs, planets in resonances, planets in habitable zones. The galaxy turned out to be more inventive than our old solar system-based imagination. K2-18b belongs to that larger revelation. It is not Earth, it is not Neptune, it is not anything we know nearby. It sits between categories, between rocky and gaseous, between habitable zone promise and sub-Neptune uncertainty, between ocean world dream and mini-Neptune caution, between biosignature hint and statistical doubt. It is a planet of thresholds. That makes it a perfect symbol for the current moment in the search for life. We are between eras too. Behind us is the era when life beyond Earth was mostly speculation. Ahead of us may be the era when atmospheric biosignatures become measurable. Right now we are in the uneasy middle, where our instruments are powerful enough to produce provocative hints, but not always powerful enough to settle them. This middle era will be messy. K2-18b is what messy looks like. A beautiful claim. A fierce debate, a cooling signal. A planet still worth studying. The emotional arc is not failure. It is initiation. Humanity is learning that the detection of life will not come gently. It will not arrive wrapped in certainty for public comfort. It will arrive through technical arguments most people do not want to read. The hard work will happen in spectra, models, calibration, and probability. The meaning will be cosmic. The method will be tedious. Both are true. A mature civilization must be able to hold both. The image of K2-18b as a Hycean world remains powerful because it gives the imagination a place to stand. A large planet under a red star, with a hydrogen atmosphere and possible ocean beneath. It feels like a new category of habitable world. Even if K2-18b itself is not habitable, the Hycean idea may still matter. Other planets may fit the model better. Future telescopes may find stronger candidates. The collapse of one signal does not destroy a class of worlds, but it does warn against turning candidates into conclusions. A candidate is an invitation to investigate, not a discovery. The difference is the difference between astronomy and myth. K2-18b has become a myth in some corners of the internet. The planet where JWST found life and scientists are being cautious. That is not the truth. The truth is colder and more interesting. JWST observed an atmosphere. Some molecules appear supported. A possible sulfur feature was interpreted by some as DMS or DMDS. Other analyses challenge that interpretation. The biological case does not meet the required standard. No cover-up, no secret. No alien ocean confirmed, just science doing what science does when the answer matters. It is tempting to resent that process because it slows down wonder. But wonder without correction becomes fantasy. And fantasy, once broken, leaves less behind than disciplined uncertainty. Disciplined uncertainty can grow. K2-18b may still teach us. Future observations may clarify its atmosphere. The planet may become a benchmark for models of sub-Neptunes. It may reveal how hydrogen-rich atmospheres behave around red dwarfs. It may show how hard trace gas detection really is. It may help define what future missions need to do better. A failed biosignature can become infrastructure for a real one. That is not poetic consolation. It is how science accumulates power. Every error that is understood becomes a tool. Every overclaim that is corrected becomes a standard. Every disputed signal that is dissected teaches the next team where not to slip. The next K2-18b will be judged against K2-18b. That is its legacy. There is a quiet scene at the heart of this story that has nothing to do with headlines. A distant star shines. A planet crosses it. A telescope, floating far from Earth, measures a tiny change in infrared light. That light has traveled for more than a century. It left the system when human history was elsewhere, crossed interstellar space, entered Webb's mirror, and became data. Inside that data, we tried to read a planet's atmosphere. That is astonishing. Even if the life signal fails, it should not be forgotten. We are disappointed because we can now ask questions that would have seemed impossible not long ago. Disappointment is a privilege of progress. Earlier generations could only wonder whether distant stars had planets. We now argue over molecules in the atmospheres of specific worlds. The distance between those two positions is enormous. K2-18b did not give us life. It gave us a sharper sense of what searching for life will demand. It demanded better language, maybe, possible, tentative, candidate, consistent with, not confirmed, not sufficient, requires more data. These words are not weak. They are the vocabulary of honesty. The public often wants science to speak like a verdict. But frontier science often speaks like weather over the ocean. Shifting, partial, dangerous to simplify. The truth is not always in the most exciting sentence. Sometimes it is in the caveat. K2-18b is a caveat with a planet behind it. That caveat matters because biosignatures are uniquely vulnerable to wishful thinking. When a scientist detects sodium or water vapor on a hot Jupiter, few people turn it into a worldview. When a scientist mentions a gas associated with life, the entire cultural machinery of loneliness wakes up. The claim becomes bigger than the data. This will happen again. A future telescope may detect oxygen and methane on a rocky exoplanet. A team may report seasonal changes in a gas. Another may find a combination of molecules that looks difficult to explain without biology. The public will hear life. The papers will say candidate. Critics will respond. The debate will unfold. K2-18b gives us a script for how not to lose our minds. Care about the possibility. Respect the doubt. Wait for confirmation. Do not let the headline become the evidence. The search for life beyond Earth is not only a scientific project. It is a test of our collective patience. K2-18b tested that patience and found it wanting in some places. But the scientific community did better. It did not simply accept the most exciting interpretation. It reanalyzed. It questioned. It published disagreements. It forced the claim into the open. That is the healthiest part of the story. Science is not a chorus. It is an argument with rules. The rules are what make eventual agreement meaningful. If life is ever found, skeptics will be part of the discovery. Their objections will have been defeated by evidence. That is how the claim will become strong enough to change history. K2-18b did not defeat the objections, so it remains a warning. At the same time, there is something profoundly human in the original excitement. It is easy to mock people for hoping too much, but the hope itself is not foolish. The universe is vast. Planets are common. Chemistry is everywhere. Life arose on Earth early enough to make many scientists wonder whether biology may not be impossibly rare. The search is reasonable. The longing is reasonable. The mistake is not wanting the answer. The mistake is taking it too soon. K2-18b almost gave the shape of an answer. Then the shape blurred. The blur is where the story truly lives. Imagine looking at a message through fog. At moments you think you can read it. A letter appears. Then the fog shifts and the letter becomes a stain. Another observer says it is not a letter at all, only a shadow. You step closer, but the wall is 124 light-years away. You cannot touch it. You can only gather more light, that is K2-18b, a possible word in fog. The word might be life, it might be chemistry, it might be noise. For now, the honest reading is not life, the planet remains in the fog. That fog is not only observational, it is conceptual. We do not fully understand sub-Neptune atmospheres. We do not fully understand all possible abiotic production pathways for molecules in exotic environments. We do not fully know how to distinguish a Hycean world from other scenarios with limited spectra. We do not fully know how red dwarf stellar activity contaminates every transit observation in practice. There are fogs inside the models too. When a retrieval code fits a spectrum, it does not literally open the planet. It searches through possible atmospheres and asks which ones match the data. But the answer depends on what possibilities are included. If a molecule is missing from the model, another molecule may take its place. If clouds are simplified, gas abundances may shift. If the temperature profile is assumed incorrectly, the inferred composition can change. A model can be honest and incomplete. That is why independent teams matter. They make different assumptions. They use different pipelines, they stress test the same data. Agreement across methods builds confidence. Disagreement exposes fragility. K2-18b produced too much fragility. That is the sober truth. The life signal did not become stronger as more critical eyes examined it. It became more contested. The interpretation depended on choices that were not universally accepted. Other explanations remained available. The claim did not reach the kind of robustness required for biology. The signal did not die because people disliked it. It weakened because evidence is heavier than desire. There is dignity in letting it weaken. The universe may be full of life, but if we cannot distinguish life from noise, then we have not found it. A false yes is not better than an honest not yet. In fact, a false yes is worse, because it steals the future moment when the evidence may truly arrive. K2-18b's not yet should be protected. Not yet means the search continues. Not yet means the planet is still worth observing. Not yet means Webb has opened the door to questions that future missions may answer with greater force. Not yet is not failure. It is the true sound of the frontier. The frontier rarely sounds like triumph. It sounds like arguments, revisions, errors, and better instruments. It sounds like researchers saying the data are consistent with one model, and others saying the same data do not require it. It sounds like excitement, followed by caution. It sounds like a headline cooling into a paper trail. K2-18b gave us that sound. A life signal that fell apart is not the opposite of discovery. It is part of the terrain discovery must cross. If we want the real thing, we must endure the almosts. The almost may be numerous. Almost oxygen, almost methane disequilibrium, almost DMS, almost seasonal variation, almost an ocean, almost a biosignature. Each one will draw attention, each one will demand scrutiny. Some will disappear, some will persist, a few may grow stronger. The real discovery may be one almost that refuses to die. K2-18b, at least for now, is not that one. But it taught us what refusal must look like. A real biosignature should not depend on one fragile spectral region. It should not vanish under reasonable changes in data handling. It should not require assuming the most life-friendly planetary model while alternatives remain viable. It should not outrun the ability to rule out abiotic sources. It should not be strongest in press language and weakest under independent retrieval. It should harden under attack. K2-18b softened. That is enough to step back. The stepping back is painful because the image was so compelling. A red dwarf system, a distant sub-Neptune, a possible Hycean ocean, sulfur gases associated with marine life. It felt like a cosmic echo of Earth. Not a twin, but a cousin. A world where life might have taken a different path under a different star. Maybe such worlds exist. K2-18b just has not proven itself to be one. The distinction between possibility and proof is the thin line holding the entire field together. Cross it too early, and science becomes storytelling. Refuse to approach it at all, and science becomes timid. K2-18b stands on that line. A planet can be both overhyped and genuinely important. That is difficult for the public but normal in science. The same observation can be valuable and not conclusive. The same molecule can be exciting and unconfirmed. The same planet can be a promising target and not evidence of life. The universe does not sort itself into simple categories for us. We have to become comfortable with mixed truths. K2-18b is a mixed truth. It is a distant world in the habitable zone of a red dwarf. It is larger than Earth and unlike any planet in our solar system. It has atmospheric evidence for important carbon-bearing molecules. It has been proposed as a possible Hycean world. It has hosted claims of possible DMS or DMDS. Those claims have been challenged. The evidence for life is not sufficient. Every sentence matters. Remove the last one, and the story becomes hype. Remove the earlier ones, and the story becomes dismissal. The full truth is harder and better. The search for life beyond Earth has always lived between wonder and rigor. Wonder asks the question. Rigor keeps the answer honest. K2-18b showed what happens when wonder gets ahead, and how rigor pulls it back. There is no villain in that, only the work. The star continues to shine. The planet continues to transit. Webb continues to collect light from distant worlds. Scientists continue to argue over spectra. The public continues to hope. And somewhere in all of this, the standards improve. That may be the quiet victory. The next time a molecule appears in the atmosphere of a distant planet, the questions will come faster. How strong is the detection? What are the systematics? What other molecules could explain it? Does the planet's environment make biological production plausible? Are there abiotic pathways? Is the host star contaminating the signal? Do independent teams recover the same result? Does the claim survive different binning, different reduction pipelines, different retrieval frameworks? These questions may sound like obstacles. They are the path. K2-18b's signal fell apart because the path did not hold. Future signals must do better. That is not pessimism. It is preparation. Somewhere in the galaxy, there may be a planet whose atmosphere really does carry the chemical imbalance of life. It may orbit a red dwarf, or a sun-like star, or a star we have not yet studied closely. It may be rocky, it may be an ocean world, it may be stranger than either. Its biosphere may be microbial, global, hidden, or seasonal. It may not resemble Earth except in the deep logic of chemistry and persistence. When we find it, the evidence will still be hard. The lesson of K2-18b is that hard evidence must be welcomed, not feared. If the signal is real, scrutiny will strengthen it. If it is not, scrutiny will save us from believing too soon. That is the bargain, truth in exchange for patience. The planet that almost looked alive has not lost its value. It has become a mirror for the way humans search. We saw a faint chemical possibility, and revealed our hunger. Then we watched science cut that hunger down size. The hunger remains. It should. Without it, no telescope would be built, no transit would be measured, no spectrum would be analyzed late into the night. No one would spend years trying to read the atmosphere of a planet. No human will ever visit. Hope is the engine, doubt is the steering. K2-18b needed both. The story ends, for now, not with an alien ocean, but with a colder and more durable image. A spectrum on a screen, lines and uncertainties. A feature that once seemed to point toward life, now surrounded by question marks. Behind that spectrum is a real planet. Behind that planet is a red star. Behind the red star is a distance so vast that the light itself feels ancient by the time it reaches us. And here on Earth, we are learning how to ask the question without breaking it. Are we alone? K2-18b did not answer. It only showed how easily an answer can be imagined, and how hard it will be to earn. That may be the most honest kind of wonder left to us. Not the wonder of believing we have found life, the wonder of knowing that we have not, and still looking.